Today, we will discuss solvent extraction as a method for separating radionuclides. Solvent extraction is defined as the process of transferring a substance from any matrix to an appropriate liquid phase. It is also commonly called liquid-liquid extraction, and it is based on extractions between two immiscible fluids, like oil and water. So, say that you have irradiated a target material which was a liquid target, or you have dissolved your target material. You then start with a target solution containing both the target material and the product radionuclides. If you choose to perform solvent extraction to separate the product from the target material, you add a second liquid which is immiscible with your target solution. If this is an aqueous solution, the second liquid could for instance be an organic phase. The immiscible liquid phase is then selected in such a way that it will preferentially extract either the target or the product radionuclides. Because the two phases are immiscible, you can then separate the organic phase, which in this case contains the radionuclide, from the aqueous phase containing your target material. Often, a back extraction step is required to transfer the radionuclides back into an aqueous phase for further use in processing steps, for example in the production of radiopharmaceuticals. This can be done by contacting the organic phase with a back extraction solution, for instance a strong acid, which extracts the radionuclides back into the aqueous phase. After separation of the two liquid phases, the final product will consist of the extracted radionuclides in the aqueous phase. The target solution is still unmodified and could be used for target recycling. The components in the immiscible phase that are responsible for the transfer of the solute, for instance the radionuclides, from one phase to the other are called the extractants. There are a few advantages to using solvent extraction in radiochemistry. It's a relatively fast method, especially compared to column chromatography, highly selective to the solute of interest, and scalable. There are several methods that can be used to transfer the solute from one phase to the other. In the case of simple inorganic compounds, such as the nonpolar iodine in this example, the solvent itself can act as an extractant. Iodine itself is highly soluble in the nonpolar tetrachloromethane, which can therefore be used to selectively extract iodine from an aqueous solution. When the two solutions are mixed by shaking, the iodine dissolves in the tetrachloromethane. After phase separation, the organic layer containing the iodine can be separated from the aqueous solution. A second type of solvent extraction is chelate extraction. In this case, one of the two immiscible solvents contains a chelator, a molecule that very specifically binds to the to-be extracted solute. If we zoom into the interface between the two solvents, we see that initially the aqueous phase contains both target atoms and product radionuclides. The organic phase contains chelating agents, which can be selected in such a way that they specifically bind to the metal ion of interest. When the organic phase is brought into contact with the target solution, the chelators form a stable, uncharged complex with the radionuclide. This complex is poorly soluble in water, but highly soluble in the organic phase, causing the metal chelate complexes to transfer to the organic phase. The two phases can then be separated from each other. How effective your solvent extraction method is can be described by the distribution ratio. This quantity is calculated by dividing the concentration of solute in the organic phase by its concentration in the aqueous phase, and is therefore a measure of the distribution of the solute between the two phases. For radionuclide production purposes, it is often important to not only consider how well the radionuclide is extracted, but also to which extent it is separated from the target material. The separation factor is a measure to describe the separation of two elements from each other in a liquid-liquid system. It is calculated by dividing the distribution factor of one of the elements, say the radionuclide, by the distribution factor of the other. Let's look at an example. You have irradiated a zinc liquid target in a cyclotron to produce gallium-68, and you separate the two using solvent extraction. After the extraction procedure, you find the concentrations of zinc and gallium in the organic and aqueous phase as displayed in the table on the right. You then want to calculate the two distribution ratios as well as the separation factor. The distribution ratio of zinc can be calculated by dividing the zinc concentration in the organic phase, 0.01 molar, by its concentration in the aqueous phase, 2 molar. The distribution ratio then comes out to be 0.005. Similarly, the distribution ratio of gallium is equal to 160. The separation factor can then be calculated by dividing the two distribution ratios by each other and equals 32 times 10 to the power of 3. Equipment used for solvent extraction requires an option to mix the two phases to increase the contact area, increasing the speed of extraction, and a method to separate the two phases afterwards. Historically, separation funnels are often used for this purpose, although, as we have seen during this lecture, you can also mix the two phases in, for instance, an Eppendorf vial, and then remove one of the phases by pipetting. However, both these options still require a lot of manual handling, which makes them difficult to automate. This is why researchers are now investigating the possibility to use microfluidic devices to separate the two phases. These look like the chip on this slide, where the red line represents the organic phase and the blue line the aqueous phase. Both phases can be pumped through the device continuously. Due to its small dimensions, the two phases can flow next to one another without mixing, and at the interface we see again the transfer of one of the solutes to the organic phase. It will be exciting to see what the future holds for the separation of radionuclides from target materials using solvent extraction. One thing is for certain, it has definitely deserved its place amongst radionuclide separation techniques.